Hello, I'm Sumin Han. Welcome all to our presentation. It's an honor to present our paper in this workshop titled Robustness Comparison of Vision Transformer and MLP-Mixer to CNNs. This work is done by Philip Benz, Chaoning Zhang, Sumin Han, Adil Kazif, and Inso Kwon. We are from RCB lab at KAIST from South Korea. In our lab, we have a group of researchers actively working in the field of adversarial machine learning. We sincerely reach out collaboration in any form. You are welcome to join what we are doing. Just drop us an email. We'll openly share our recent ideas. If you have cool ideas, we can also do your ideas together. You are also welcome if you are just a new master or undergrad. Here's a list of 20 selected papers related to adversarial machine learning since 2020. Now let's start it. Let me briefly introduce the different architectures we are comparing. Convolutional neural networks have become the de facto gold standard in a variety of computer vision tasks and are attracting interest in a wide range of domains for several years. CNNs consist of multiple building blocks such as convolution layers and pooling layers, and they are locally connected and sharing weights by convolving kernels. Therefore, the shift invariant property lies in the structure and design of CNN. On the other hand, fully connected network reacts differently to an input image and its shifted version. In other words, each node has a different weight and it is not shared. Fully connected network ignores the information brought by pixel position and correlation with neighbors, and therefore cannot handle translation, that is, shift variant. Self-attention-based transformer was firstly introduced in 2017 and have provided superior performance in translation and their applications in natural language processing. It is noticeable that they can nearly match human-level performance on various NLP tasks when applied with pre-training. Vision transformer, as known as VIT, is built on the same transformer architecture, and the critical distinction is in the pre-processing layer for the image. This layer divides the image into a series of non-overlapping patches and then uses a linear projection to reconstruct the image. That is, VIT feeds the linear embedding sequence of these patches as inputs to the transformer. This is obtained by a process known as two-dimensional convolution, in which the number of filters decide the hidden scale of the sequence input to the transformer. Additionally, VIT prefixes the input with a separate CLS token whose representation is used for final classification. In MLP mixes, there are two MLP blocks in one layer, and each MLP block clearly separates the operation from given location, is known as channel mixing, and operations between different locations, we call it patch mixing, respectively. Using two MLP blocks, one is used to perform operations between patches, and the other is used to perform internal operations within a patch. Mixer borrows design choices from recent transformer-based architectures. The design of MLP blocks used in Mixer originates from transformer, which substitutes the self-attention model with multi-layer perceptrons. Further, converting images to a sequence of patches and directly processing embeddings of these patches originates in Vision Transformer. MLP-Mixer has a quite simple and intuitive structure which requires less training time due to less complexity than VIT. However, it has limitations from MLP that requires a large amount of data and input must be a fixed length. Classification is one of the most fundamental tasks in machine learning. Various deep classifier architectures had been introduced in the past, of which the performance of a few is shown here. One fundamental concern about deep classifier is their robustness. Previously, it has been shown that deep classifier are vulnerable to adversarial examples. Adversarial examples are small perturbations in the image, which are specially crafted to deteriorate performance, which can lead to misclassifications and to be mostly imperceptible for human observers. One of the earliest and simplest adversarial attack methods is the fast gradient sign method, which simply calculates the gradient with respect to the input image, takes the sign, multiplies it by a certain magnitude value, and adds it to the image. As shown in the example, through applying such a tiny perturbation, the network is full to misclassify an image of a panda as a gibbon. Although CNNs have been significantly successful, they remain vulnerable to adversarial examples whose small additive perturbations of the input cause the CNN to misclassify a sample. Due to the rather recent introduction of the VIT and mixer architecture, the adversarial vulnerability of these novel architectures has not been well studied yet. This work sought out to explore and analyze the adversarial vulnerability of VIT and mixer architectures and compare the findings against the CNN models. In our experiments, we mainly compared the VIT models, MLP-Mixer, and resonant architectures. For the VIT models, we consider VIT-B and L16, where B and L stand for base and large, respectively, while 16 indicates the patch size. The considered VIT models were pre-trained on ImageNet 21K and fine-tuned on ImageNet 1K. Corresponding to the VIT models, we also investigated Mixer B and L16, except that these models were directly trained on the ImageNet 1K without additional pre-training. We further considered the ResNet 18 and ResNet 50 architectures trained on ImageNet 1K, as well as the semi-supervised variant, which is pre-trained on a subset of unlabeled YFCC 100 mega public image dataset and fine-tuned with the ImageNet 1K. And the semi-weakly supervised variant, which are pre-trained on 940 million public images with 1.5K hashtags, matching with 1000 ImageNet 1K synthets followed by fine-tuning on ImageNet 1K dataset. To evaluate adversarial attacks, we evaluate different adversarial attacks in the targeted setting on an ImageNet compatible dataset composed of 1000 images in 430 classes. This dataset was originally introduced in the NeurIPS 2017 Adversarial Challenge. We used this NeurIPS dataset for all experiments we did here. We provide the experiment result from 4 tasks: robustness against white box and black box attacks, for example, and frequency analysis. The level of knowledge the adversary possesses generally falls into one of 3 defined categories. In a white box setting, the adversary has access to all the information of the target neural network, including its architecture, parameters, gradients, etc. They can make full use of the network information to carefully craft adversary examples. This table shows the attack success rate under white box attacks PGD, FGSM, CW, and default. Overall, a trend can be observed that compared with CNN architecture, the VIT and mixer models have a lower attack success rate, suggesting they are more robust than CNN architectures. This is further confirmed by finding that CNN requires a relatively lower L2 norm for the CW and default attacks. One exception to this observation is the mixer model, which appears to exhibit increased vulnerability to very small perturbations, being as vulnerable as the CNN models for an epsilon equals to 0.1. In the black box attack setting, the inner configuration of the target models is unavailable to adversaries. Black box attacks assume the lowest level of adversary knowledge, generally only allowing the final classification to be known without any finer details about the model. Adversaries can only feed the input data and query the outputs of the models. The usual approach is to create some substitute model that can generate the adversarial samples instead. Compared to white box attacks, black box attacks are more practical in applications. We use the boundary attack as a query-based black box attack, which works by evaluating a sequence of perturbed images through the model. For a non-targeted attack, the starting image can be sampled from uniform noise. The method modifies the image iteratively to look more like an example from other class while continuing to preserve its adversarial nature. The intuition behind the boundary attack is to slowly move to the direction of the decision boundary and do random walk along the boundary. We can see from this table that a trend can be observed in the black box as with the white box attack that the VIT and mixer models are more robust, indicated by the relatively higher L2 norm of the adversarial perturbation. Here We report the attack success rate under a transfer-based black box attack which exploits the transferable property of adversary examples. That is, the adversary examples generated on a source model transferred to another unseen target model. For the source model, we deploy the iterative FGSM attack and evaluate the transferability on the target model. From the resulting table, we have two major observations. First, adversary examples from the same family or similar structure exhibit higher transferability, suggesting models from the same family learn similar features. Second, when a different model architecture is used as the source model, there is also a trend that CNNs transfer poorly towards foreign architectures. For example, the transferability from CNN to VIT is often lower than 20%, while the opposite scenario is much higher. In the previous white box attack, we observed that VIT and MLP-Mixer are more robust to adversary examples than conventional CNNs. To facilitate the understanding of the mechanisms, we designed a toy example of binary classification where each class is only represented by a single image with a size of 224. The two images consist of a single black stripe on a gray background, differing only in the orientation of the stripe, namely a vertical and a horizontal stripe. We then trained three different architectures on the toy examples. We designed the network to be of relatively small capacity, the number of parameters to be less than 5 million due to the simplicity of the task, and to constrain the networks have around the same number of parameters. We evaluate the adversarial robustness of these models with the commonly used L2 attacks, CW and DDN. It can be observed that the CNN is also less robust than the FC and the VIT in this toy example setup. Here are the figures for the adversary examples and their perturbations under CW attack on three different models. For the VIT, one phenomenon can be observed that the adversary perturbation consists of square patches. This is likely due to the division of the input image into patches in the VIT architecture. Without the split process on the image, we observe clear stripes but with different patterns for CNN and FC. While the CNN model generates perturbations with repeated stripes, the FC model generates perturbations with only a single stripe in the middle. It should be noted that perturbations are generated toward the adversary, that is, in the direction of the opposite class stripe. The observation that the CNN model yields stripes all over the image can be naturally attributed to the shift invariant property of the CNN model. From the perspective of shift invariance, CNN model recognizes features, that is horizontal or vertical stripe in their setup regardless of the position of the features on the image. Thus, it is somewhat expected that the perturbation has stripes in a different direction all over the image. For the FC model without the shift invariant property, it only recognizes the stripes in the middle. Thus, the resulting perturbation mainly has a stripe in the middle. The invariance to shift leads to greater sensitivity to adversarial attacks. This qualitative result suggests that the reason for CNN being more vulnerable can be partially attributed to its shift invariance. Future work is needed to further establish the link between shift invariant property and model vulnerability to adversarial attack. We further attempt to explain the lower robustness of CNN from the perspective of frequency. For the low-pass filtering, an earlier and sharper decline of the CNN architectures can be observed than for the VIT and Mixer, indicating that the CNNs are more reliant on the high-frequency features. For the high-pass filtering, the VIT model shows the steepest decline among the models, indicating that the VIT models rely more on low-frequency features. Note that non-robust features tend to have high-frequency properties and attribute to decreased model robustness. This indicates why VIT models are more robust than CNN architectures. When results from both low-pass and high-pass filtering are compared, it is observed that mixers, regardless of their absolute value of accuracy, exhibit a similar trend to CNNs rather than VITs. Here are the summary and takeaway messages from our paper. We did an empirical study on the adversarial robustness comparison of VIT and MLP-Mixer to the widely used CNN on image classification. We provide empirical results for the white box and black box adversarial attack, toy example on binary classification, and frequency analysis for the low-pass and high-pass filtering. We could conclude from the result that, firstly, VIT is significantly more robust than CNN, and Mixer is generally located between VIT and CNN. Second, the lower robustness of CNN can be partially attributed to the shift invariant property of CNNs. Lastly, VITs are more reliant on low-frequency features, while CNNs are more sensitive to the high-frequency features. So, this is the end of our presentation, and thank you for listening.